So the thing I've learned is, if I had guessed that these 5 digits are correct, I've now learned that they are not. If I guessed that these first 2 digits are correct, 1 negative 1.63, maybe that is the case. I'm not sure, and I won't be sure, but I can do this a few more times with even more specific values to give myself confidence that these 2 digits are correct. For now, having done 2 in a row with these 2 digits still correct feels like good evidence. I guess I haven't seen... I've had 2 digits that stayed the same for a while. I guess I'm pretty sure it's negative 1.6 something. The 3 might still change, but probably it's not going to change all the way to the 6. So we can't compare our answer to the true correct answer, but I can compare this pretty accurate one to that even more accurate one and see if... watch the digits slowly stabilize as I make more and more computations. The homework doesn't give you that many things where you do it over and over, but once in a while... if you do need to feel confident about how many digits are correct, you just keep computing until those digits stop changing. And that's when you feel like they're probably correct. This is what the derivative is. The reason we cared about the derivative... So, this last slide I gave the definition of the derivative. The reason I did that is because I was finding what is the fly's speed at a moment. In general, or more generally than that, f prime at a point gives the rate of change of a function at a point. If I'm in a context where I've been talking about average rate of change, and I want to emphasize that this one is not an average rate of change, I might call it an instantaneous rate of change. To emphasize, this isn't the rate over a period of time, this is the rate at a particular instant. This can do lots of things, the units, oh hey, this is worth saying. The units of f prime at a point are always in y units over x units. I computed it by taking a difference of y values divided by a difference of x values. Subtracting those inches gave inches on top. Subtracting those those seconds gave seconds on bottom. That last example wound up with inches per second. If I had a function that was giving me a number of tacos as a function of how many days has it been, then the derivative of that function is going to tell me something in a rate of tacos per day. It's always going to be y units over x units, whatever it is. There's going to be lots of applications of this. Let's try another example. So let's try an example of this. Let's say the population of some town is given by, or maybe is modeled or is approximated by P of t is 14,000 e to the 0.03 t. And we want to ask the question, where t is in years since 2000. Our question is, how fast was the population growing at the start of 2020? And the answer to this is a derivative. How do I know the answer is the derivative? They're asking how fast is something changing. That means it's a rate of change. And the time that they're asking is not a period of time, it's a moment in time. It didn't say how fast was the population growing over the course of the year 2020. It was at the start of 2020, which is presumably a single point in time. So we're asking for what is the derivative at some point. The question is, what's the point of that is the start of 2020? Well, time is being measured in years since 2000. I guess we assume that means since the start of 2000. Which means the start of 2020 is exactly 20 years later. We want to know what is p prime of 20. How do I approximate p prime of 20? I say it's about p of, I need a number very close to 20. I'll go with 20.001, I guess, minus p of 20 divided by 20.001 minus 20. The number on bottom I can subtract myself in my head. These two numbers on top are, plug 20.001 into here, so 14,000 e to the 0.03 times 20.001 minus, now plug in 20, 14,000 e to the 0.03 times 20. And now, what is this? I get digits on this with a calculator. Dear calculator, what is 14,000 e to the 0.03 times 20.001 minus 14,000 e to the 0.03 times 20. I don't need to wrap this up in parentheses because this is all one thing. There's not multiple things added together. And now divide that by 0.001. And I get an answer of 765.3. P prime of 20 is about, I'm going to round that to 765. How do I make a sentence out of this? 765 what's? Well, remember, the units are always y units over x units. Our y thing is p. P was population. So the y units population is measured in people. Come on, wake up, stylus. I gotta pause this and fix my stylus. Okay, our y units are people. And then our x units were t units were measured in years. So at the start of 2020, the population was growing at a rate of 765 people per year. Does that mean at the end of 2020 the population will be 765 higher? No. It would mean that if the average rate of change over the course of the year was 765 people per year, we only know this is how fast it was going at the very beginning of 2020. So if it had kept going at the same speed, then at the end of the year there would be 765 more people. But we know things change their speeds. So maybe it was speeding up, maybe it was slowing down. We could ask some more questions and figure that out. But we just know how fast it was going at that moment. So right, that's computing derivatives from a function. Let's try an example that does this in other ways. When you're teaching math, there's a pedagogical thing that you should try to explain something with a sentence, with a formula, with a chart, and with a graph. Let's try the chart version of this. I'm going to hand you a function that you don't have a formula for. And let's say this is 15.4. This is 16.2, 16.8, 17.3, 18.1, 19.2. And if I told you to approximate f prime of 8, what are we doing? A chart kind of turns all this stuff on its head. The thing that the derivative we said just a second ago was f prime of 8 is supposed to be, I need to take f of 8.001 minus f of 8 divided by 0.001. Well, this doesn't make sense.